Okay, so we've talked a fair bit now about the anatomy of the skin and the accessory structures associated with the skin. So now it's time to talk about the skin's role in maintaining body temperature. So heat is produced by the body. It's a byproduct of the metabolic reactions that occur in the body. And so the organs that are the most active, those are the organs that are doing the most metabolic work, are producing the most heat. Skeletal muscle is our primary heat producer. And even when we're inactive, so even in sleep, skeletal muscle is producing anywhere between 20 and 30% of body heat. But when we're active, it creates way, way, way more. The active skeletal muscle produces a huge amount, 300 to 400% more than all the other parts of the body combined. The heart is also a big producer, because it's constantly active, it's also a big producer of heat. And then the liver, as well as any other glands that are actively processing and doing work, will also are also up there in producing lots of heat. And the term for organisms, animals that maintain body temperature at a specific level is that they are homeothermic. So homeothermic, that means warm-blooded. That's the warm-blooded is the common term for that, but homeothermic is a much more precise way of saying that. And we regulate our body temperature to somewhere around 37 degrees C, or 98.6 if we look on the, can't underline, there we are, if we look on the Fahrenheit scale. So where is body temperature regulated from? Well, that's up in the thalamus, and so I have a picture here of a cadaver that's been sliced, and the hypothalamus, I may have said thalamus, I meant hypothalamus. The hypothalamus is the organ that is responsible for maintaining body temperature. Hypothalamus is here in this region, just below the thalamus. This where you can see my pointer is circling the thalamus. So when we get to the anatomy of the nervous system, we're going to look closely at the brain and see all the parts. So, and this brain, because it's been preserved, the shape is odd. It looks a little smushed as if it's been lying back. Normally it would be filling the entire space, that entire void inside the cranium. But anyway, I think that's enough to say about that. So it's the hypothalamus that controls our body temperature, and the reason that it's so important for those organisms that are homeothermic, to have body temperature control, to maintain homeostasis around body temperature, is because all the metabolic activities that are controlled by enzymes occur properly at the appropriate body temperature. And so if body temperature gets too high, then all those enzymes that are working, they actually can speed up for a time. But if it get really high, then they will stop entirely. So those enzyme-controlled reactions will break down because the enzymes themselves break down. We denature the protein enzymes, and we're no longer able to run those reactions anymore. And neural activity also becomes depressed. So if the body reaches about 41 degrees C, that's 106 in the Fahrenheit scale, then we're looking at convulsions, those febrile seizures. If we get greater than 43 degrees C, that's about 110, then we're looking at death, because we have completely denatured many of the proteins that are running those, the enzymes, the protein enzymes that are running those chemical reactions. So what do we do then to lose heat? So let's look at some of the ways that the body loses heat. The first means of losing heat is through radiation. Radiation is the transfer of heat in the form called infrared. So we lose infrared radiation from the body. What is infrared? If you've ever been in a bathroom, like at a hotel, that has the heat lamps up in the ceiling. Or if you are at McDonald's and you check out where they're keeping the fries, where they're keeping them warm, they use heat lamps that send out a significant amount of infrared radiation. And so the lamps in the infrared lamps are often reddish colored. And that produces heat waves. And so up to 50% of the body heat is lost via this radiation, by heat waves that come off of the body. Conduction also removes heat from the body. It can also transfer heat to the body. Imagine now if you sit down with your bare butt on a cold tile floor. Very soon your bum becomes icy cold too, and that's because conduction has transferred heat directly through that contact with the cold floor. And so we conduct heat from the body. Convection can also remove heat, and so that's the reason we turn on ceiling fans or we blow fans across us. Even if the air temperature is really warm, just by moving the air, we can move heat away from the body. Or if it's really warm air that's blown across your body, then it would add heat to the body. But usually we think about convection as taking heat from the body. So air can do that. Or if you were to go into a swimming pool or a cold stream or river or the lake, then convection would also carry heat from the body, and pretty soon you'd be chilled. And then the last way that we remove heat from the body, and this only removes heat from the body. It doesn't give heat back to the body. We can radiate heat to the body. We can conduct heat to the body. We can convect heat to the body. But evaporation only takes heat away. And evaporation occurs when water on the skin's surface changes state. It changes from being liquid to being gaseous. And in that process, it takes a lot of energy to change water from liquid to gas. And so in that process of evaporating at the surface of the body, water takes away a lot of heat from the body. And it turns out you don't have to be in a cool environment for evaporation to cool the body. What is required, though, is that the relative humidity be low enough that water can evaporate. So on a really humid day, water doesn't evaporate easily, and we produce a lot of sweat, but it doesn't do much to cool us. It just winds up soaking our clothes. Whereas if we were in the desert on a hot, dry day, it could be 110 degrees in the desert, but we would feel cooler, perhaps, even than a 97-degree day in a humid area, because water would be able to evaporate from the skin surface, taking heat from the body. So if the body registers, the hypothalamus registers that we have become too hot, that's hyperthermia, hyper meaning greater than, then the dermal blood vessels dilate, and that brings warm blood from the core of the body out to the surface of the body. And then sweat glands secrete sweat, and the heat that is radiating from the dermal blood vessels will evaporate the sweat. And in the process of evaporating away, the water in the form of gas, then takes heat from the body. And we bring the body temperature back into homeostasis. So, quick question, what kind of feedback would that be? If, here we are, body's gotten, here's homeostasis, would be here, and then we go out and work in the hot sun, and so we get warm, and then we sweat, stop working, but we're sweating, and we return to homeostasis. So what kind of feedback came into play right there? Take a moment, turn off the video for a second if you need to, think about it, and then come back. Okay, so if you're back with me, hopefully you thought negative feedback. That's the kind of feedback that we would expect to bring the body back into homeostasis, because we're reversing. We were getting warmer, but we turned around and got cooler again. Good. So the opposite can happen too. The body can become cold. So how do we gain heat in the body? Well, as I said before, you can gain heat through radiation, conduction, and convection. So if you go take a warm shower, or a warm bath, then convection will warm you up. If you go stand in front of a hot, stove, and there's radiant heat coming from the stove, then radiation is going to warm you up. But the body also generates heat internally, as we've said. But in many cold environments, this may not provide sufficient heat to keep us warm. So if we're still cold, even though we've tried to warm up through radiation, conduction, or convection, and we have our internal heat, well, then skeletal muscles throughout the body will contract. And that provides some additional heat. Remember, even at rest, some of the skeletal muscle is contracted, and that's providing heat to the body. If we're still cold, then we get rhythmic contraction. So now we get much greater active contraction, and this is what we talk about as shivering. And shivering can produce lots of heat, and hopefully then negative feedback will return body temperature to homeostasis. And again, hopefully you remember that this is homeostasis. We get cold, well, negative feedback will bring us up to being warm again. Because remember, we're getting cold, negative feedback reverses the direction. All right, so that's how we gain heat. So now let's talk a little bit about wounds and how we deal with wounds to the body. So inflammation is the primary response that the body has to damage or injury of some sort, or an infection. And inflammation is caused by the mast cells as they release histamine and heparin, the two chemicals that they produce. So the signs and symptoms of inflammation include redness. So it becomes red. It becomes warm, local heat. Swelling occurs. And then we also see pain. This would be the symptom. All the others, these are the signs. And the difference, if you don't know, the difference between a sign and a symptom. A sign is something that a healthcare provider can observe, measure, touch, feel, know that way. A symptom is something that the patient would have to tell the healthcare provider. So if something is painful, if they feel dizzy, those would be symptoms. So what's the effect of histamine and heparin? If you recall back from when we talked about the tissues, histamine causes dilation of the blood vessels and makes the blood vessels leaky. Heparin prevents blood clots. So the redness, the heat, the swelling that we see all directly relates back to histamine and the effects of histamine. And all that swelling, plus chemicals called bradykinins, I'm not going to worry about that one, that are released by damaged tissue, those chemicals and the swelling presses on pain receptors and causes the painful symptoms. And so here we see a person who is suffering chilblains, they're called. And it's just a symptom, or it's an inflammation that occurs when body parts get really, really cold, and it causes damage to capillaries, and so that results in this inflamed response. And I chose this picture because you could see the redness very well, and clearly you can make out the swelling, and you can probably imagine what that would feel like if you put your fingers to it. You would feel that heat coming off of it. And then finally, the patient would likely report that there's a fair bit of pain going on. So why inflammation? How does inflammation go about promoting healing? Well, it does a couple of things. First, it brings in macrophages. Remember, these are those white blood cells that do a lot of eating So they're the big eaters. So it brings in these macrophages to the injury site, and they help to remove whatever the harmful agent is. All that swelling helps to isolate the damaged area. So the circulation out of the damaged area is slower, and it gives time for the macrophages to do their work. So it helps to reduce the risk that injury might spread. I almost think of the swelling as being like a quarantine, where you prevent things from leaving, or at least slow them down enough that the macrophages can get involved there. And last of all, the dilated blood vessels are going to bring oxygen, going to bring nutrients into that area to help speed repair. So inflammation can be helpful. And that slight increase in temperature in the area will even kind of speed up the activity of the macrophages and the fibroblasts that are going to be moving in to do the work of helping to heal the wound. And then last of all, when we think about healings and cuts, I've given you in your notes package a fair bit of information. And so what I suggest is that you read the notes package, you read the books, and use the drawings. And I've got the drawings here for you to remember, or to recognize which drawings I'm suggesting you go look at, to look at how healing occurs in cuts. So here's a damaged area. Blood pools in that damaged area and begins to clot. So clotting is important. And then in this clot, fibroblasts move in. Macrophages also move in. The macrophages start removing the blood clot. The fibroblasts start rebuilding connective tissue. And then from the edges, we get epithelial cells swarming in to cover it over and to help recreate all the layers of the skin. So finally, by the end of it, there's new blood vessels growing through the area. There's a significant amount of connective tissue replacing it, and then just a thin little scab toward the top that is slowly being eaten away at the bottom by the macrophages. And so by the time the scab comes off, you've got a whole new skin surface there with a bunch of layers already in place, protecting the body from any invasion. So again, for more information, I want to encourage you to read the information in the book about healing, because you can expect some questions about healing. And I think that's all that I want to say here. I'm just noticing, there's the term granulations. So granulations appear in wounds, and these granulations are just little masses of blood vessels and fibroblasts that are all working together to help rebuild the connective tissue there. And so when we talk about a wound showing granulation, that's a clear sign that healing is on the way. Okay, so we'll leave it at that, and I'll see you with the last section coming up, talking about burns.